Okay, let's get started. Welcome to this training workshop. And so for today, we're going to cover how to use Google Engine Cloud Computing. So how many of you have used Google Engine before? Not yet? Okay. You have you used JavaScript, Python, or what your experience is? Both, okay. And do you have an account already? Google Engine account? Okay, great. So, and if you can go to the website, the projector is not very clear. But if you go to geemap.org, and then on the left side, click the workshops. And then if you scroll down to the bottom, you should be able to find TNGIC 2024. Can you see it? So this is a notebook we are going to use. And there are two ways you can follow through. You can use Google Colab just to run the notebook interactively using the browser, or you can also choose to install on your local computer. So if you already know how to use Python, you can run on local computer. But it doesn't matter. So for most of you, I would recommend just right-click here, open in Colab, and then open link in the new tab. Then you should be able to open this one in the Google Colab. So for those of you who are not familiar, Google Colab basically is just like a cloud computing environment, allows you to write Python code and execute, and then kind of like Google Document, but it's for writing text. This is for writing source code. And you need to log into your account. So upper right corner here, if you have not logged in, you need to log into your account. Otherwise, you won't be able to use it. And then on the left side here, there are a couple buttons I want to introduce. So the first one is the table of content. So the upper left corner. So if you click, you can navigate through. This is a pretty long document. So sometimes if something doesn't work, you might need to reboot the notebook, and it's better to navigate through. Sometimes you might want that. So this is the first one. And the other one here on the left side, on the lower left corner here is the file. So this one allows you to see the files that we generate when we're running the source code. You can also connect to your Google Drive. So it'll be useful later if you want to save some of the output from. This is basically a temporary computing environment. Once you close the tab, the browser is gone. So it's temporary. It's not saving anything to your computer. And if you really want to save it, you can connect here. You can connect to your Google Drive if you want to, but you don't need to. It's not a requirement. So you see after click the button, it's going to basically add a code block somewhere here. And let me zoom in a little bit. You can run it if you want to, but like I said, it's optional. So I'm going to delete this one at the moment. Also on the left side here, there's a kind of like a key. You see this one? So this one is called the environment variable. And so anytime you're using Google Engine, you need to authenticate. And sometimes it's a bit annoying because you need to click a couple buttons all the time until you can get to run the source code. So if you want to save time, you can create a so-called a token here. For now, we can just ignore it because I will show you the step how to do that. But if you're someone that's going to use this all the time and you're very annoyed by Google Engine that you need to click the authentication every time, then this one will save you some time. But if you're beginners, you don't need to worry right now. It's not going to affect you too much. So here, once you open this notebook, and the first step I want to recommend is to change the, if you're using the dark mode, you want to switch to the light mode because some of the tools do not work very well right now in the dark mode. It works fine, but it just looked a little weird. So if you want, you can go to the settings here, upper right corner. And then from here, once this pops up, there's a sim here. So you can select the light one. Select this light one. You can continue to use the dark mode if you really want to. It's fine as well. But I would recommend just switch to light mode for the time being. You can switch it back after you finish this workshop. Okay, so this is the first step. And after that, we can start executing the source code. And like I said, this is a very long document, and we're going to go through step by step how you can actually run the code as long as you already have the account. So the first one here, we're going to do is to install the packages. And Geemap is actually already pre-installed in Google Colab, so you don't need to install it if you're just using the core functionality. Since we're using some additional functions that not available in the default Geemap package, so you can remove the hashtag at the beginning, or you can press Control/ on your computer. So put your cursor within this code block, and then Control/. I think my the keyboard shortcut is occupied. Or you can just remove it. Remove the hashtag at the beginning. And then on the left side, just click this button. This Run Cell button. It will ask you to just click Run anyway. And it should take less than a minute to install all the dependencies that require for this notebook. If you run into any issues, just raise your hands. We can slow down. Any problems? So go to this code block. So you scroll down to the beginning here. This one, install Geemap. And there's a hashtag at the beginning. Just remove the hashtag. There's a command. And then you just run this button. And at the bottom, it said successfully install blah blah. Then you're good to go. And this one has a long log. You can on the left side here. You can hover over your mouse. Oops. You used to be able to just remove the output. Anyway, something is wrong here. Okay, once it's done, then you can navigate to the next step. So we're going to click this button here. So for all the code blocks, you can press Control Enter, or you can just click this button. So it's up to you. So you can, for example, I can press Control Enter. It's the keyboard shortcut. It should be able to install the package. No, import the package. Okay, import the libraries, and then click this one here, Geemap.ee_initialize. So this is basically we are going to authorize our account to connect to the Google Engine server, so that we can do cloud computing. So just run this button, and you probably won't see this one because I have the secret tokens stored on my notebook in here. And for you, you probably, let me cancel, then you should see this one. All right? Do you see this interface? Yes? Do you get any errors? Does it work? If you see this screen, then you click this link. It's open another tab in your browser, and then it's going to ask you to authenticate. So you might see an interface like this. Make sure that you have a cloud project somewhere in here. Choose a project. So if there's a star and there's no project in here, probably you won't be able to continue. So you need to choose a project, or you need to create a new cloud project if you don't have anything in there. So if it is empty for you, you can create a new cloud project. Just accept all the default settings. You'll probably be fine. So for me, I already have one here, and then can just click the generate token button. Do you see this one here? I might EE books something. Used to be something different. Any issues? If not, you can just click generate token. And then it's going to ask you to log into your account. So you want to select whatever email account that you're using. So on the right here, I'm going to select my account, and then click allow. At the bottom here, you should be able to see the authorization token. So there's a copy button here to the right, and just copy. Then come back to the notebook, and in the input box here, place your cursor inside, then Control V, and then just hit enter. And it should say save authorization token. If you see this one, that means you have successfully authorized your notebook to connect to Google's engine. Is it working? Good. Raise your hand if you run into issues. Okay, let me see. You need to pass this one, otherwise we won't be able to do anything after. Make sure that you successfully connected. Can you go back to the your browser tab? Go this one. To be kind of your IT just missing. No app. Just no. Is it working? You have the error message. And again, run the code on the next. Here you just generate tokens. Set your account. Thingy. No bad. Select all. The copy button. Go back to the and the info box. Paste here. Probably because your account is not. Probably your. You need to. You also get an error. So run it. See if you get any error message. Recording. You guys have any issues? Okay, you execute it successfully. So if you have went through the authentication, you can run these two code blocks. So if everything works fine, you should be able to see the map. If you cannot see the map, that means something is wrong. You need to fix it. So this is the step that you need to get to. And let me pause the video here a little bit. Okay, so once it's successfully authenticated, then you see the map. And before we get into Google Sending, we're going to quickly, for example, how to create maps with some custom options. So for example, by default, it's going to create a map like center around 0° longitude and also 20° latitude, zoom level 2. But you can customize the center. So for example, if you want the map to center around the US, you can pass in a parameter center equal to, and this is the latitude, this is the longitude, and the zoom level, and also the height. The height, basically the map height, 600 pixels. So you can change it to the smaller one. You can customize it. You can do whatever you want. For example, you can change to 400 pixel, and then you can control enter, run again. It will generate a new map, but right now it's a little bit narrower. And you can also change the center, right? So if you how about where are we right now here? So for example, I can zoom in somewhere to here. Let's say you can center the map somewhere around Nashville if you want to. So for example, right, somewhere here, let's say, or you want to center the map here, and you need to find out the center and also the zoom level. So what I would recommend, if you don't know where it is, you can create a new code block. So on the left side here, click this code, and then you're going to create an empty code block beneath the map here. So we name the map M. So basically it's object-oriented programming language. So if you type M and then dot, wait for a couple of seconds, it should pop up a list of options. So basically M is an object, and object has properties. You can also apply any methods. So basically it's representing this map. So the map has center. So if you type center, it should pop up, and then you can just select, hit enter, and then control enter again, or alt enter or something like that. You should be able to see this one, right? So basically this one tells you right now what's the map center. And similarly, I can create another code block, and you can type m.zoom, and then if you type command enter or alt enter, it will show you the zoom level. So this is basically how you get the map center and also the zoom level. And then you can go back to change the map. So if next time if you create a map, you want the map to by default to center around this location, I will just do this. Okay, copy this one, select it, and then Control C. Then you can come back to the map in here and just replace this one. replace the center with whatever you want, right? And then Control V. And also the zoom level. What's the zoom level for this one? 14. Okay, so just type 14 and then run it. So you should be able to see the map right now is centered around this location. So basically the map is kind of like when you open Google Map using your phone or something, you're going to center around your IP or something like that. So you can also do that, something like this. But for now, we just hard coded the latitude and also the longitude and also the zoom level. Then you can create a map. You can change the height. There are a lot more things you can customize. Next one, if you run this code block in here, it's going to show you the map. So go back to this previous one. If you click the left side here, upper left, this one is called the source, the data control that allows you to source data. I will show you how to use it later. We also have the zoom control and zoom in and zoom out. But you can also just use your scroll wheel. You should be able to zoom in and zoom out interactively. And also on the left side here, full screen, and also some dual control, some buttons in here allows you to create, for example, object, select anything. We cover this one later. So this is the dual control. Up right here, there's also a toolbar control. So this one has a lot of interactive widget that allows you to change things. So if you click the button here, and then on the left side here, there's a hamburger icon. If you click the hamburger icon, this one shows you you can turn layer on and off. So there's a checkbox there if you want to turn things on and off. Okay, and you can also change the slider, change from the left to right. It's going to change the opacity. So this is basically is interactive, allows you to change all the data layers displayed on the map. We cover more later, but for now, just show you some of those interactive widgets. And the next one here, I can actually hide all those controls. So sometimes if you feel the map is too crowded, you can remove stuff. So I can remove the, for example, all the dual control and those two buttons, upper left and lower right. But if you don't want any control, you can also remove it, all of them. So here, if you create a new code block, okay, and then just type m.clear controls. And if you run this code block, look at pay attention to this, all the controls right now on the map. So if you run this one, and we come back, you see, all the stuff, all the controls on the map are gone. So you can think about the map is just like Lego. Everything on the map is a widget. It's something you can add, you can remove. Everything is customizable, and even the layers, you can also remove the layer. So for example, if this layer you don't want the layer anymore, you can also use clear m.clear layers and hit enter, parentheses, and control enter. You see right now is all the layer will be gone. So allows you to add layer on the fly, remove layers, add control. So anything displayed on the map is just like different components. You can put things in, you can remove things if you don't want them anymore. So that's about the simple base map. And so earlier, let me run this one. The example show you basically use the OpenStreetMap, but you can change the base map to something else. If this you don't want the OpenStreetMap. So for this one here, we passing the base map parameters, and then we specify the Esri satellite imagery base map. So now you're seeing the satellite imagery rather than the OpenStreetMap. And similarly, I can go here, and you will see now this one is the Esri base map. So there are lots of base maps available. There are different ways you can specify, but for this one, if you just want the satellite imagery, you can do it like this way. You can also add a base map later. So once you create a map, right now we have the Esri imagery base map here. I can add another one. So this function is called map.add underscore base map. I can add the topo map, for example, like this. I can add another open topo map, right? And it's going to see all the data layer going to add to the previous map that we specify. And you should be able to turn this all the data layer on and off. And then you can change the opacity, left. Can you adjust it? Questions? So this is right now no cloud computing yet. It's just simple web map services. So allows you to pull any web map from the internet and then add to the Basemap. And so for Geemap, there are lots of Basemaps available. So if you click, for example, here, if you click this range icon, and then second row, first column, this button here, if you click that, this one's you should be able to see all the Basemap available. So there are hundreds of Basemap available that you can directly access. You don't need to write code. So for example, if you need, how about the CartoDB dark matter, if you click that, you should be able to switch the Basemap easily from here. And how about, for example, the ESA work global link cover? Right. So there are over 100 Basemap available. This is not something you can do using the Earth Engine JavaScript code editor. In Python, it's a lot more flexible. So, and for example, I can also load the original satellite Basemap. For example, 2021 Sentinel-2 two color composite. Right. So you have access to this imagery without having to download the data. And all the imagery, all the map in here, right? All the names, for example, NLCD 2021 lane cover. So if you select that, it should be able to load the lane cover similarly. So all you need to do is just figure out the name. And then if you want to do that programmatically, you can just simply map.app basemap. Scroll down here, just passing the name to here. And then you should be able to add the Basemap programmatically if you want to. Also, if you want to see the list of maps, like right now it has 145. And I'll show you the first 10, for example, right? So any names in here, if there's anything you like, you can just select this one. Something like this. And then Control C. Then you can come back to whatever app Basemap in here. Replace it, Control V. And then just run that code block. You should be able to see the map being added to here. Again, this is just simple Basemap. It's not cloud computing yet. It's just web map services being loaded to this interactive map. Questions? So with the basic about the map, now next we can get into cloud computing. So, and Google's engine is very powerful. So you can think about if you are new to this, the reason we are using this is now a lot of data in the cloud. So we used to go to, for example, NASA, USGS to download the data, and then you open ArcGIS, MV, and then start doing all the data processing. It's fine if you're doing that for a small area, but if you're doing things at a global scale, it's become more and more challenging because the data storage is huge. You need terabyte storage to download images for the entire globe. And even if you can store the data, you cannot really compute because you need a lot of memory and CPU, GPU, and it's become very computational intensive to do things at the global scale. And Google's engine is exactly what we need for this kind of cloud computing because you don't need to worry about how much data storage you need. You don't need to worry about computing power. Everything can be done in parallel, and it can be speeded up with tens of thousands of servers. So how it works is basically think about the cloud computing. It has tens of thousands of servers, and when you're doing something, it's subdividing your area into smaller pieces. And it's sending one piece to one computer, the other piece to the other computer. And that small piece, right, if you have one server to handle, it's very fast. So you can basically distribute the task to tens of thousands of servers. And you can get the result back in seconds. So you can, and then you're going to merge the result. So the reason that you see the map in here, I just wanted to make sure you understand. When you zoom in and zoom out the map, sometimes if the internet is slow, you're going to see it's popping up piece by piece. I'm not sure if you encounter that. This is basically what under the hood it's doing. It's sending those smaller pieces to each server. And when it's sending back the result, it's going to combine all together. Looks like seamless, but it's not. Each server is handling a small piece. And this is why it's so powerful, so fast that It's not a single computer. It's tens of thousands of servers working at the same time for the area. And so Google Sensing has some data types similar to desktop GIS. So these are the 5 basic data types in Google Sensing. Image. Image is pretty simple. It's just a single image, and a single image can have multi-spectral band. Image collection means basically it's a bunch of images. You can think about a bunch of images on within a folder on your computer. And so for Google Sensing, one sensor sometimes is one image collection. So an image collection can contain just one image. It can contain 10, 100, 1,000, a million, 10 million. It doesn't matter. It's basically most the images share some commonalities. For example, all the landscape A images, surface reflectance, or TOA or anything, all the modes belong to the same sensor. It can be one image collection. And the geometry is just like in a shape, like a shape file without the attribute, just the shape. It's called geometry. And the feature basically is one shape with some attribute. Okay, you can think about one feature is one row in a shape file, right? When you select one, open that in ArcGIS or QGIS, you select that and then you can highlight. A feature collection essentially is a shape file, a bunch of shapes, a bunch of geometries with a bunch of attributes. And so these are the corresponding kind of data type to the traditional GIS data type. So the first one we're going to look into is the image. Okay, so if you just run this one, this code block is going to show you. And so all the Google Sensing object is under this EE something. Okay, when you see EE something, that means it's Google Sensing, Earth Engine something. So it's Earth Engine image, image collection, geometry, feature collection. And what essentially it is it's on the server, and you are basically pointing to the data set, but you don't actually store the data set on your computer. The data set is in the cloud. So you can think about this is like you're watching a Netflix movie, and each Netflix movie has a unique ID on there. And basically just pointing to that movie. I want to watch that movie. So what we're doing here is pointing to that DM. So this is SRTM. And that SRTM can be several gigabytes, can be tens of gigabytes. It doesn't matter how big it is. You're just pointing to the data set. And then you can print it out. So here you can show the properties. You can see how many bands in there. So for this particular image, there's only one band. It's called elevation. And you can see the coordinate information. You can also see all the metadata. And you also have the link in here. If you want to click, you can click to look at more information. And these are all basically a bunch of metadata. The provider and the image, the size, something like that. So allow you to basically look at the data. And this will be something like you go to Netflix and then click and watch the movie. You see the cast, the characters, the plot, the summary, something like that. The same thing. So we don't actually download the data, right? You are watching a movie online, but you don't actually download the file to your computer. You are streaming on demand. So we're doing the same thing here. So once we have this data set, next let's see how we can actually see it. And if you run this code block, it's going to load the data and let's load the DM. So take a look at this. So now we have this DM loaded on the map. We don't actually download it. We just stream the data on the fly. So we are watching, basically we're streaming geospatial data from the Google Sensing cloud server. And you don't need to download the data. It's so fast because this one, if you need to download this to a computer, it's going to take you maybe hours because it's many gigabytes. And now I can just zoom in, I can zoom out, I can take a look. So if you go back to the code block, and we can quickly go through like what this one is doing in here. First line, create a map, right? Simple, right? You create the map centers around somewhere and then zoom level. And the next one is that we are pointing to this image. So image. And you can think about this one is the unique ID, okay? You can think about it's a social security number to every asset in the server. And usually it's the provider and then slash and then the name, okay? And after that, this is the visualization parameters. So Google Sensing is unlike desktop GIS. You can open the imagery and then right click and then property. You can change the symbology, something like that. The Google Search Engine itself doesn't provide that functionality. And Gmap has, I will show you later. But what it's doing is like, I want to visualize this imagery, and I'm going to set the minimum and the maximum. So this is basically when you're trying to stretch the imagery. And also you can specify the color palette. So basically how you want to visualize the imagery. And this one, we have a few 5 color in here. So this is called hex color code. It will be 6 digits. The first two will be R, red, and then green, blue. Okay, so each color is represented by 2 digits. And hex color code means it ranges from 0 to 255. So it'll be 0 to F. And you don't need to remember this. There's much easier way. But basically what you're doing is, okay, I have this imagery. I want you to visualize that using the minimum 0, 6, maximum 6,000, because the elevation, okay, we know the maximum is around 8,000. But you can set to a lower number if you want to. And then after that, just add this layer. So map.add layer. And then the first one will be the object you want to visualize, how you want to visualize that. And the third one is the layer name, okay? And after this, you should be able to, for example, you will run again, you should be able to see the same result. And upper right corner here, you can click this one and then click this hamburger icon. You can turn the layer on and off. You can also change the opacity, something like this. And you can zoom in, you can zoom out. So what we're doing here, we are streaming the data from the cloud, and then we can, if you don't want to remember this color palette, you can just remove it. So let me show you here. Remove it all the way, and then I can just change it to terrain, for example, and run again. See? It's a different color. So this is kind of like in ArcGIS, you change the symbology. And there are many options. For example, I can change to full warm. So any name. So if you know Python, if you have ever used a matplotlib, the matplotlib color map, you can apply anything in here. So it's super flexible. You just need to know what you want to do, how you want to do it. There are many color available. For example, I change to maybe green. If the name doesn't exist, it will throw the error, and then you will know that it doesn't work, right? And you can also change the, for example, maximum to 4,000, right? So you're going to see differently. So what this is doing is changing things on the fly. And of course, because we are focusing on the area at a global scale, so if you change to a lower number, you're going to see a lot more white color, because anything greater than 4,000 is going to be white color. But if you change to a large number, it's going to be, for example, I change to 7,000. Then you want to see more variations in higher, in this area, right? So now it's not white color because it's not all the pixels are greater than 7,000. Make sense? So this is how you stream the data, and for one single image. A better way would be like this. So if you really want to, for example, if you don't know what to do, you just load the imagery. So by default, assume that you don't know what to provide. You just know, okay, I want to see this imagery, and I want to see it. For this one here, assume that you don't know what the parameters. So you can just pass in an empty one, empty curly brackets. That means they're using the default. And if you run this one, it's going to show you like something like this. Grayscale. It doesn't look fancy. It's not very good. But you can load this one, and then let me show you how you can change the color. So you can click this button again, and then click the hamburger icon again. Here you should be able to see this settings icon. Click this one, and it should pop up and dialog allows you to change the color. So here I can select, for example, I want the colors just like what I showed you earlier, right? These are all the names of the color available. So I know this one is the elevation, so I can change it to terrain. Okay, and then hit apply. Not so good, right? It's all white color because the maximum here is 100, right? So I can just change it to 4,000. Hit enter. Run again. See? So this is kind of like in desktop.js, you can change the symbology interactively. You can also use the slider if you want to, but here you can just change to 4,000, 5,000, 2,000, whatever you like. And if you want a different color, I can change the color. For example, a screen, apply, and everything is running on the fly, it's on demand. So what it's doing is sending the request to the server and then ask it to return the result of your cast, whatever you want. You need to specify the options that you want. And after that, you can just click close, then you're good to go. So this is for one single image. Next, let's talk about so-called the image collection. Because there are lots of data available there, you need to know where to find the data, how to filter the data. So let's use the Sentinel-2 as an example. Similar to the image, this one here is e.image collection. So that means we are pointing to the entire satellite image collection. And then we assign this one to available. So we're using the Sentinel-2 surface reflectance. And this one has a lot of images in there. And so if you want, you can run this code block. So what it's doing is taking the entire Sentinel-2 image collection and then take a so-called median filter. So this one has tens of millions of images in there. It's going to take a while. It might not show up. It used to be okay, but now it takes a much longer time because there are a lot more images in there. So it takes a while to return the layer back to the map. So what we want to do actually is run this one. It's a little bit better because we can filter the data. So you see this one now is much faster compared to the one above. So let's take a look at this one here. So this is the entire Sentinel-2 image collection, and we can actually filter by date. So you can select images that within a specific date range. So this one here, we're selecting images in 2021, right? The year, month, and date. And then you can continue to filter. We can also filter by cloud cover. So e.filter.lt, LT means less than. So we are selecting cloud cover less than 5%. So essentially this code block, what it's doing is, okay, give me images acquired in 2021 with cloud coverage less than 5%. All the images at the global scale, and all the images in 2021 less than 5%. And then it applies this one called the median filter. Median means you might have a bunch of images taken for the same location throughout the year, and you take the median. Basically means like you have all the DM values, the pixel values. I take the median for all the same. For example, bang 1, I take the median of all the bang 1, all the time series. So the reason taking a median is pretty good because if this cloud, the value will be very high. For low values, it will be very dark. So somewhere in the middle is usually pretty good. It's not cloud. So if you look at this one, right, and then we take in a composite. So right now, you can see the images. Looks not bad, right? You can zoom in, you can see more details in there. And this is at the global scale, so you can zoom out to anywhere. So, okay, so right now, see there? Do you see when I zoom out, it's popping up. It's not all at once. It's block by block. So see again. And this is going to take a little bit longer because the way you zoom out is going to basically subdivide into small pieces, and then you're going to pop up piece by piece. And this is where the cloud computing parallel processing is subdividing your area into smaller one, and then you can send to different server. So if your internet is a little bit slow, you will see some kind of artifacts. But this is totally normal because it's not processed by the single computer. And think about here, if you need to download images at a global scale, and you need to do all the processing, this is going to take you hours or days to process. And what we're doing here essentially is seconds, right? Although it takes time to store up, but it's still so much faster than the traditional way. And you can zoom in. So if you're only working on a small area, it's pretty fast. It's usually seconds compared to hours and days, to process the same data set. So this is using the Sentinel-2 image collection. You can do the same thing. So you can use Landsat, you can use MODIS, you can use any satellite, and the workflow is pretty much the same. So you just figure out what image, what satellite you want, and then figure out what date do you want, and then what area you're working on, and then also the metadata, basically cloud cover or a specific year, month. They're all kind of functions. We don't have time to cover all that, but you just need to think about what do you want, and then you figure out those criteria, and then you just put all those everything together. It's basically all the conditions. You can filter, you can narrow down until you get to what you want. Questions? Okay, next one, feature collection. So the feature collection is basically vector data in Google Engine. And so let's run this code block, and then we can talk about what it is. So this one, we are pointing to the Tiger 2016 raw. So this is the census data for transportation network. So if you can zoom in here, this is a huge data set. It's for the entire US. And what we're doing here is pointing to this data set, and then just add the data layer without any customization. You see here is just one line of code, pointing to the data and just see it. If you need to download this one, it's going to take you a while. It's many gigabytes, but this is at the national scale. You can zoom to any location you like. So this is a huge vector data set available for the US. And you can also do the filtering. So similarly, we're going to load, for example, data set for US states. And you can filter .eq. EQ means equal. So because the data set has attributes. And this one basically is similar to desktop.js, select by attribute. For example, I want to select the state, name, Louisiana, right? And it's going to select the data set, and then you're going to select this specific one. So how do we select this one? Select a state for this one, the US states, right? Have all the state boundary for all the states. So how do we select one for Tennessee? Easy, right? Just the name equal to Tennessee, then you should get Tennessee. So for example, I should Tennessee, NESSEE. You can change the layer name if you want to. For example, TN, and run it again. See, get Tennessee, and you don't need to change many lines of code. So pretty much you can just one line, and then you get fixed. Now you can easily get the data you want. So for example, how about maybe New York? Okay. Okay. So you can get any states you want. You can also get multiple states if you want to. So next time, if you need to find some data, vector data, you don't need to go online to source everywhere. Google Engine has a lot of data sets. So all you need is just to point into that entire data set, and then you can specify a small area. You can specify the date or time, whatever you want. Then you can get the data, and then you can start doing the computation. So here, if you run the second code block, this one shows you, for example, all the attributes associated with the feature that we just selected, right? So the FC, basically this is the feature collection. Doc first means you select just the first one. Kind of like in the swap file, you select just the first row to see what's in there, right? So you see this, all the attribute, you see the name, you also see all the attribute associated with this. If you need to select multiple, so for example, you want to select your study area is the West Coast, you can also use this. So this line is the same. So you can think about this is the US states vector data. And then you can just apply this function called doc filter. Doc filter means I want to select by attribute. And then inside we have the e-doc filters in list. In list means if you are inside this list. So if your name is either California, Oregon, Washington, I'm going to select that. And I'm going to return the result, save the result as a variable, and then just add the data there, and then look at it. So now you have this, right? So pretty simple. And similarly, right, here, if you're working on, for example, Tennessee, and you want to select the South each state, you can do that as well. So if you just want to select one state, usually use e.filter.eq. If you need to select multiple, you can use e.filters.enlist. That means like if you are one of them, then you select out of that. You can also select by location. So for example here, I can do it like this. I can, from based on the map, okay, I can use these drawing tools, right? So this is more like select by location. Like in ArcGIS, QGIS, I can just select a rectangle. So pay attention here. I draw a rectangle somewhere here. Okay. That means I want to select all the US states intersecting with this one. Once you click this one, run this next code block and see what happens. You see, all the states intersecting with the area that I draw is being selected. So this is select by location. What it's doing here, this code block is going to grab whatever the draw polygons. If you don't draw anything, you're going to use this default one. And after that, there's in vector data, there's a function called filter bounds, basically filter by bounding box. And then you can pass in the area. So this one basically is the bounding box that we just drew on the map. And then it's going to narrow down and you select whatever vector data intersecting with the area and then select that. And after that, you should be able to load the data there. So these are different ways you can select vector data. Questions? Once you have this, then we can visualize. So in Google Engine, visualization is a little bit tricky. You need to know how to visualize stuff. Otherwise, by default, when you add the data layer to the map, it's going to look either grayscale, it's not going to look very fancy, but you need to know how to customize it. So for vector data, right, we have this one here, and then we use the map.add layer, and then passing the variable in here, and also this one. So if you use the curly brackets without giving anything, that means you're going to use the default visualization, and then this is what it looks like. But the nice thing about this is it allows you to inspect the properties. So once you load the data, upper right corner here, if you click the button, the first row, first column, this identify here, allows you to identify the attributes. So if you click this button, and then you come back to the map in here, you click anywhere on the map, it should be able to inspect the properties. By default, you need to click this button here and then look at the properties. So this is kind of like in GIS, you open that, you click and then see all the attributes, just like you open the attribute table. For vector data, I would recommend just check this box on the right here, click this object, so that you will be expand by default. So now you can click anywhere else, it's going to show you, right? So for example, if I click Tennessee, it's going to show you the attributes, basically the attribute associated with the polygon of the state of Tennessee, right? So you can see TN, Tennessee. If you click here, you can see Texas, right? So this is called the inspector, allows you to inspect vector data, raster data, basically any Earth Engine data. Once you're done, you can either click this button, you can hide it. You can click again, you want to open up again, or you can just close it. So everything on the map, just like widget, allows you to interact with the data. And if the default color is not something that you like, you can change it. So now if you run this one, we change the color, we change the outline color, we change the fill color. So everything is customizable. It looks a little bit not very intuitive, but this is how Google Engine is visualizing data. So for vector data, you can apply this called the style function. The style allows you to change the outline color, the fill color, the opacity, something like that. So if you pay attention to this color here, this one has 8 digits. Okay, so the first six is RGB. The last 2 digits is the opacity. So what this one is 0000 FF. That means it is what color? Red RGB. Okay, red, green, blue. So 0 means it's no red, no green. FF is like 255, is all blue. So this is why you see the blue outline in here. And the last two digits FF. FF means is the opacity fully opaque. So basically means this solid color. If you change the color, you become lighter. So in this case, for example, if you want just, you can change it to maybe 80. 80 means the color will be a little bit lighter, so it's not going to be fully break. Okay. You want this one again? Yeah, probably hard to see. This one is still, I mean, pretty dark. But if you change the fill color, this one will be more obvious. Right. So again, the fill color right now, it looks like it's like red color, and then FF means it's red, right? Green, blue, and then the last two digits is opacity. So, for example, right now, if I ask you, I want to change it to green color, fill with green color, what should we be changing? I want to change to green color. What is green color? Red, green, blue, right? So you'll be 0, 0, 0, 0, FF, 0, 0, okay? And depends on whether you want to transparent or to opaque. If you want to be fully opaque, then it will be FF. So that means it's going to be pure green color, filled with green color. And if you want to be a little transparent, if it is 0, 0, that means it's nothing. That means you'll be transparent. So right now, if you put 0, 0 inside, you want me to see the red, green color, it'll be just like this. Make sense? And 80 is roughly 50%. So if you change to something here, last two digits, 80. It's a slightly transparent, not fully transparent, but you can see the labels beneath the green color. So you can control the outline, you can control the fill color to whichever way you want. And keep in mind here, this is the vector data, but when it's transport to your browser, it's actually just images. It's not the original shape file, okay? It's everything is just PNG on your computer. You cannot really, you pointing to the original data, but we don't download the original one. If you really want to see like being under the hood, how this is working, if you can zoom in, you can zoom out. It's actually downloading those images on the fly. So here, if you go to your browser, and then on Chrome, and go to, I think, under the more tools, and then developer tools. So this one, if you want, you can actually see how it's doing. So if you look at this one here, the network, right? If I zoom in and zoom out, you see it's downloading the PNG, something.png. I'm not sure if you can see it. It's going up in here. So these are actually how the data are being transported to your computer. So if you double click any of those, you see the map, so like one small tile. This is how it's being downloaded to your computer. So if you click this one, this is the OpenStreetMap, the Basemap. Let me see if we can find the Google. Not this one. Maybe this. You see the Google Earth Sensing data there. There's like one tile by one tile. This is being returned by one server, one computer, and the map that you see here from this one, under the hood is a bunch of smaller PNGs then being put together. It looks seamless, but it's not. It's basically piece by piece. So if you zoom out, it's going to download another one. So for example, right now in here, it's already downloaded, so you don't see it. But if I zoom out or move the location, oops. Probably I already see a lot of those, so it's not showing up. But if you see all this green color, you see all the small pieces. So this is how you visualize the feature collection. So next, this one is even more complicated. So if you want to change, for example, color by a specific column, you can do that as well. And there's a bunch of visualization parameters here allows you to control. For example, I'm going to use the name column to visualize And what it's doing is going to be ranked over alphabetically of all the names, and then going to subdividing into different categories, and then going to use. So this is more like GS place maps, allows you to create a map based on the values of a column. So right now here we use the column called name, but you can use any column you like. For example, I use the column maybe A lane. Okay, I know basically the lane area. We're gonna run this one. Oops. You see, right now you are having this. So the reason for this one is because the color are going to change from this green color all the way to a little bit white color. That means you see the map like this. So this darker color means it's lower land area, smaller land area. This white color means larger land area. So basically it's like the symbology used to represent the value range of a certain column. So if this is sometimes if you want to create a map like this, you can do it easily using this code block. But you need to specify all these parameters, and sometimes it can be a little bit annoying because it's unlike GIS, you can just open and select a column and then change the symbology. Google saying is everything need to be coded, so you need to know how do I write the code to customize it. You can also change the color. So for example, here you can change it to a different color. For example, the last one I can add. For example, I can add maybe a red color. For example, then you'll be FF 0000, right? So I can add another color at the end. So that means the largest state is going to be highlighted in red color, right? So if I run this one, see, because I use the lane area is the column to create a map. So of course you're going to see all the larger states are going to be hollow because I add the last one at the end. So you're going to basically rank all the area of that column. Smaller one is going to be dark color, and then gradually you're going to see this color. So this is why it looks like this. Okay, any questions? So it's what time? Did we already run 2 hours now? Or is it 1 hour? Okay, 1 hour 15 minutes. Then maybe let's get have a 10 minutes break, and then we can come back at 2:25. Okay. Okay, let's continue. So the previous section we have covered how to create some basic interactive map, how to visualize some data. And the next section we're going to talk about how to actually find the data. So Google Sensing has a huge data catalog. Right now it has over 100 petabyte. 100 petabyte. So 1 petabyte is 1,000 terabyte. So it's 100,000 terabyte. So imagine how big it is. It's not as big as what all the NASA data has, but Google Sensing data catalog has a lot of those commonly used satellite data from different space agencies. It also has a lot of land cover data, weather climate data, you name it. So any data that you might be using, you might also already be available on there. So in this section, I want to show you how actually you can search the data. Essentially, what we're going to do is to teach you how to search a movie on Netflix, find the movie that you want, and then you just stream the data and watch the movie. But we're going to basically visualize the data. So here, if you create a new map, Geemap has a button here, upper left corner. If you click this button, and then there's a data tab here. So if you click the data, and this is where you can search all kind of data. And this is just like when you search movie. So for example, if you need any elevation, you can just type elevation and then just hit enter. Then it's going to show you a list. So there's a drop down list on the right here. It's going to show you all the elevation data in the data catalog. So there are tons of data available. So it's up to you which one you want to use. For example, I can select some of the SRTM. So for example, here there's a which one, US NED, for example, SRTM digital elevation data version 4, for example. You select one, and then here it's going to show you a small thumbnail and also some of the metadata information. If you want, you can click the link to go to the Earth Engine webpage, and you can also see what it looks like here. And there's a button, import button, allows you basically to import. So if you click the import button, it's going to show you this code block, and so it show you the sample code. This sample is already being copied to the clipboard. If it doesn't, you can just come here, select this, and then Control C. Okay. Then after that, you can either come back to the code block in here, and then hit Enter somewhere there, and then Control V to paste the source code into this map, right? Because we create the map and we add the data layer, right? So just run this one and take a look. So now we have actually have the DM. This one is calculating the slope, okay? Loading the slope to the map, and take a look at this. So now we have this entire DM being loaded to the map, and it's also running the calculating the slope. This is at the global scale, so it's pretty fast. But you're welcome to source any data set you want. There are lots of data available. So I can source another one. For example, click this one, data again, and I can source maybe lane cover, for example. And from there, you can select whatever lane cover type data you want. For example, I can try the ESA wall cover, 10-meter resolution, right? And again, you can click this import button, and this one again shows you the code block of the data. And again, it's already been copied to the clipboard. If it doesn't, you can just copy this one, Control C, and then come back to here. I can just replace the previous example and then just edit. See, so now we have this global lane cover. So any data set you want to search, just find it and then just copy the example code, and as simple as that. And then just paste it into a new code block and run it. You'll be able to see the data. So again, this data set itself is, I'm not sure how many gigabytes, it is tens of gigabytes, because it's 10-meter resolution, so it's pretty big. It's at the global scale, and now you can just stream the data easily. You can change the color, you can do all kind of things. Later I'm going to show you, for example, how to do the computation, how to do some simple zonal statistics, how to figure out, for example, which country has the largest forest cover, or which country has the largest surface water area, agriculture, urban, you name it. You can do all the computation that you traditionally do using the desktop, but it's so much faster because you can get the result within seconds, rather than you have to go online, download data, and then maybe have 1 terabyte hard drive to store the data, and then you need to think about how to do the compute. It's going to take you a while, and this is so much faster. So this is about searching the data. Also, Geemap has a datasets module. So if you're someone that you don't want to click the button, you can use this way. So the data module allows you to access the data catalog through dot notation. So what that means is, like, when I type the data and then dot, and you see here, this one has the entire list. So basically allows you to access the data kind of like a hierarchy. And this is similar to in the movie, right? You can have different movies, action movies, romantic movies, like different category. I can go to the next one. So if you already know, for example, the data set coming from somewhere, you know the provider. For example, okay, I know the data come from maybe USGS. You just type USGS. See, I'm gonna pop up, and it's gonna show you all the data that coming from USGS. Then you can look at the one that you want. For example, the 10-meter resolution. I want to look at the DM 10-meter resolution. So this one basically is pointing to the unique ID. Rather than using the /, this is using, for example, the underscore. So it's the same thing. So this basically you can access to the ID without having to memorize it, because I just type the data dot and then USGS, and then you can just select from drop down list. Then we get to the unique ID. And after that, you can just load the data. You can visualize that. So for example, this one is the USGS link cover data 2011, right? Just one line of code. You can point into the data, and then you can just visualize that, right? So this one line of code is to access the data, and this one is to just add the data layer to the map. That's it. So two lines of code. We now have this data layer for visualization. And again, you can zoom in, you can zoom out. Everything is interactive. So this is something that you can do. You can also look at the metadata information. So use the get metadata from Geemap that can show you something like this. And it's the same thing that when you source the data using this button, and then click the data. And so this one, for example, link cover, just type get, hit enter, right? So you can see this and corners, right? So you can see this one from the drop down list in here. But if you want to do that programmatically, you can also call this function to see the data set. So this is how we can source data. Okay, again, it's the over 100 petabyte. You just need to find what you want, and once you get the data, you can start visualizing it. Next example, I'm going to show you how to convert JavaScript to Python. So Earth Engine, when it got started, most of the documentation is using JavaScript, and Python was quite limited at the time. And that's the reason that I developed the Geemap package to make it easier for users to use Python to visualize the data. But if you happen to have a lot of JavaScript source code written for Google Engine, right now you want to use Python. So Geemap has some functionality that allows you to convert things automatically. So here, for example, you can go over to the Earth Engine documentation website. And nowadays, they have added a lot more Python examples. But in the past, there's mostly JavaScript. So for example, if you go here and assume this is, right now you see the Python, right? They also have JavaScript in here. So there's a button here. You can actually copy the JavaScript source code and then you can convert to Python. So just copy the button and then come back to the notebook. Upper right here, click this button. And then there's this one here, like second row, second button. This one allows you to convert Earth Engine JavaScript to Python. So just Control V here. Oops. Control V. And then click the convert button. And this is going to convert to Python. And the source code should have been automatically copied to the clipboard. Then I can just come to here. Again, add a new line. Control V. But no, it's not copied. Then I need to copy from here. So select Control A, Control C. And then come to here, Control V. And run it. Okay, so now we load the data. So what we're doing is convert JavaScript to Python directly without having to manually, because otherwise you need to know the syntax difference between JavaScript and Python. But now with this, we can just one click, you can do the conversion. And now we have this data layer, right? So this is originally from the JavaScript. Of course, nowadays they have this Python in here showing you don't have to actually convert manually. And if you click the Python setup here, Geemap has been adopted officially by Google Engine. So now if you want to use Python, you can use all the Geemap. But here it's called Geemap.core because the Earth Engine team only help maintain the core functionality. But you can just import Geemap, everything is the same. So just import Geemap, then you can start using those functionalities. So that's about converting Earth Engine JavaScript to Python. And I have an exercise in here. You're welcome to try the exercise if you want to. With this, we can continue, and then when we have the break, you can try it out later. So this exercise basically allows you to select some satellite sensor and then create some cloud-free images. So if you go back to the previous example earlier, I showed you Sentinel-2, right, at the global scale, and you can figure out what area of the images that you want, what date, what time period, cloud cover, anything. You can basically filter. So you have access to all the data. And then you just need to tell, okay, the criteria. Okay, I want the Sentinel-2. I want the data for last year. I want the data that has cloud coverage less than 10%. I want data that covering, for example, Tennessee. You can just do the filtering. Eventually, get to the narrow down to the images that you want, and then you can apply the median filter, and then you will get the images kind of mostly cloud-free for the area. So this one is probably take 5 or 6 lines of code, and you can create cloud-free images for any state, for any country, or even at the global scale. So most of the steps are pretty much the same. You just need to nail down using those filter, and then eventually just do a median filter. So this is the showing example, for example, for Texas. But Geemap has a lot more functions that can also help you create time series. So you can create time series, for example, okay, I want cloud-free images for Tennessee from 2000 to 2023. Every year, one imagery. You can also do that as well. It's just one line of code. I will show you more examples later. For now, let's just keep it here. Next example is about some visual tools that allows you to interact with the data. So the first one, we are adding some DM, landscape imagery, and also the vector data, the state boundaries. And this is how we're going to visualize that. Why is it taking so long? Is it the internet? This one? This should not be interesting. Yeah, the internet is fine, so I don't know. This one is not computation intensive, so it's not take a while to run. Did any of you finish this one? Can you run it? Weird. Let me restart my kernel, so see if it works. If you happen to restart the kernel, then you need to import the library again. You need to initialize again. Otherwise, it won't work. So let me import this again, and then go back to the plotting tool here. Okay, so this time is faster. Anyway, so this map here, we have 3 different data layers, and the last line of code here, map.add inspector. So the inspector is the one that I showed you earlier to inspect the vector data, but you can also inspect raster data. And by default, it's adding this one. So right now, if you hover your mouse on the map, if you click somewhere, it's going to get all the pixel value. For example, we have a DM, we have a landscape imagery, we also have vector data, right? So if you click your mouse on the somewhere, it's going to get, for example, if there's no polygon, it's going to get the elevation pixel values and also the landscape, the spectral bands, right? So we have this one, we have 6 spectral bands in here. So it allows you basically inspect the pixel values. So this is just the identifier and to get the pixel values. It's different from desktop.js because the imagery is on your local computer. So you can use the mouse to inspect pixel values. But Google Things is different because the imagery is not on your computer, it's on the server. So under the hood, it's getting the mouse coordinates and then it's sending the coordinates to the server, doing the computation and then return the result. So you see it's not instant. It's pretty instant, but it's going to take less than a second. It's sending a request, run the computation, get the result back. So if you click somewhere that has the polygon, you will see the polygon. If you have too many data layers on the map, you don't want to check some of data layer, you can turn it off. So for example, I just want to inspect the DM. Then you can turn off other data layers. Then if you click your mouse on the map, it should just show you the DM values, right? So if you hover your mouse, you can click continue to get the pixel values. If you just want the, for example, the landscape data, you can turn out the layer off. Then this will just show you the pixel values for the spectral signature for the location that you selected. So this is for inspecting Earth engine data. Another one is called plotting tool. So this one is also useful, especially if you're interested in looking at the spectral signature. So we have two data layers. The first one is the Landsat data layer. The second one is the hyperspectral, Hyperion. And this is how I'm going to visualize it. And there's a function called map.plot GUI. So on the right here, you're going to see the drop-down list. So we have two data layers. One is the Landsat data. The other one is the Hyperion. So they just use the Landsat data, select the Landsat data. Then you can hover your mouse on the map anywhere. So if you click your mouse somewhere, it should show you this one. So this is the spectral signature, right? So if it is vegetation or if you click the water, it should not have two. This is a bug. So if it happens, you can run this one again. Let me see here. For me to fix the bug. So okay, it's still happening anyway. So allows you to, for example, let me select here. Right, so this one is just the water. So it's the water, the spectral signature is decreasing. But for vegetation, it's different. You're going to have high reflectance in the near infrared band, right? So it looks like something like this. You can also try the hyperspectral. Let me run this one again. And let me select Hyperion from the drop-down list. And you can zoom in to see the hyperspectral data here. This looks like a little bit cloudy, but this is actually hyperspectral data. So if I click right now on the map, you should see a line like this. So because it has over 200 spectral bands, so it's much denser, so you're going to see all the points. And you can also customize the plot, right? So if the color is not something that you want, you can, for example, run this one. Let me run the next one. Okay, so you can add the marker cluster and also change the plot to a bar chart. So if I run this one again, you see now I have the bar chart rather than the point. Right now it's showing the duplicate. Again, this is a bug right now. I just need to find a way to fix this. It works fine locally on Jupyter Lab, but it's on Google Colab. It's a little bit tricky here. So this is how you can do this spectral signature for multispectral data, hyperspectral data. Next one, legends. So if you use desktop GIS, most likely you're familiar with some of the legends. And I'm going to show you this one. I'm going to show you the lane cover, for example, right? So allows you to create a legend, something like this on the right. And you can just use one line of code. So this one shows you add the Esri Basemap, and then also add the NLCD Basemap. Then we have this add legend, and there's a built-in legend called NLCD. So if you go back to the top here, so Geemap have some built-in legends. So just one line of code, they can create a legend. And so this is what this one is about here. You can, if this too much, you can hide it. You can click this again, it's going to open it up. So this is so-called the legend, allows you to see different lane cover. So it's useful when you are doing especially lane use lane cover. You want to show what each color represent. Then you can have this one showing up on the map as a widget. So that one is using the NFCD. This is just the base map, but we can also use the Google Sensing data. So Google Sensing also has lane use lane cover data, and it's very much similar. So this is the unique ID pointing to the NLCD data, and you just add the data layer, and then after that you add this legend, right? Built-in legend, NLCD. You can change the height. So it's the same thing basically, but the data layer is different. Okay, the previous example is the base map. You cannot use it for computation. This one is the real Google Sensing data. So this one you can actually use for computation. We will show you some example how to do computation later, but for now, we just add the legend corresponding to the lane cover. Besides the legend, you can also customize. You can pass in a list of colors and a list of keys. So this example here shows you it's pretty simple, right? A legend with 5 color and then 1, 2, 3, 4, 5. So it depends on what color you want to use. You can change the color, you can change the label. So the real world example would be like this. If you click the next one, this is again the same thing, but right now it's customizable because I can change the color. You can change the label. So this is the label, and on the left side here, this is the color. So if you pay attention to this one here, is a dictionary. So you can pass in a dictionary when you are trying to add a legend. So this is the source code here, this one, and this line is adding a legend. So if you, for example, if you don't like, how about this, open water? You don't like open the water, you just want water, then you just remove open, right? You can. So basically everything showing on the map, that legend, you can customize it. If you run again, then it's going to showing up here right now, showing you it's water, no open water. So everything or every label, you can change it if you want to. And this is great because, for example, if you're someone looking at the lane cover and you want to see, for example, let me zoom in right now to somewhere here. Okay. Can you tell me what's this lane cover? This color here, my mouse? It's hard to tell, right? Because color very much similar. So what you can do is just go to your mouse and then click this inspector. Okay, and then just click the mouse on the map. It's going to show you this one, right? Lane cover 71. And then, oops, where's my mouse? Okay, so 71, then let me, okay, I cannot see my mouse. Then you can open this one. Okay, 71, so grassland. Of course, right now this one is a little bit narrow because it's kind of a the laser overlay on top of the pixel inspector. But if it's something that you want to inspect all the time, you can change the height of the map so that it's much higher. So I can say height equal to maybe 800 or something like that. So then the map would be higher. So in that way, it will not block the legend. So look at this one right now again, right? So I can zoom in here one more time, right? So how about this yellow color? What's this? I don't know, right? Use the inspector. Press your mouse. Okay, lane cover 81. What is lane cover 81? Partial hey, right? So allows you basically inspect. So again, you don't, the data is not on a computer, the data is in the cloud. So what you're doing is when you click your mouse on the map, the program is getting your coordinates and it's sending the coordinate to the server and then run the computation and then check the pixel value and then send it back so that you can see that on the pixel inspector. For example, here, right, the red color, if you click it, this is 24. So 24 will be develop high intensity. Okay, so that's about the legend. The next one is about the color bar. So color bar is for continuous data. The legend is for discrete data. So lane cover data, classification, then you want to be discrete. Color bar is more like continuous. Temperature, elevation, something like that, right? So this one, look at the bottom right here, we have this one. So this is so-called the color bar. That means we add the color bar to represent the range of the elevation. So from 0 to 4,000. So, and essentially just one line of code. So the previous lines we are already familiar, right? So the image, how we want to visualize that, and then add the data layer, and then next one, the last one is to add a color bar. So the color bar, you can use these visualization parameters. So it depends on how you want to visualize that, right? So if you look at this one here, we use this color palette and then we add the color bar. If you change the visualization, it will change the color bar automatically. So that you don't need to change a lot of lines of code. So for example here, I can remove this one. Right now I have 5 hex color code. I can just change it to maybe terrain. And if you run again, the color bar will be updated. So look at now, we have this updated color bar here with the new color. I can change it to maybe, again, cool, warm, and run it. See, it's being updated automatically. So makes it really flexible. and easy to use. If the color bar by default is horizontal, you can also make it vertical. If you run this one, see, now it becomes vertical color bar. You can also make it transparent. So you can add this one, transparent BG equal to 2, basically transparent background. Okay. It doesn't work in Google Colab, but it should work locally on Jupyter Lab. So this is about the color bar. Next one is about the split panel map. So split panel map basically have a slider in the middle that allows you to swipe through. So if you have two data layers you want to compare side by side, then you can use this slider. So if you just move your mouse left and right, you can see that. And this is just one line of code. So think about it. If you're using JavaScript or others to develop this, many hundreds of lines of code. But in Python, it's pretty easy. So I can also zoom into a certain location, and then I can use the slider to swipe through. So this example only use the Basemap. So this is not Google sensing data. The next example here shows you how you can create a split map with real Google sensing data. So what you need to do is to point to the Earth Engine data, and then use the Geemap.e tile layer to get the layer, and then you can pass the layer to the left and also the right in here. So it's only basically 3 lines of code, then you can create this split map. So here you can zoom to, for example, let's look at Las Vegas, right? So I'm looking at this data layer. On the left side is 2001, on the right is 2021, right? So it's about 20 years difference. So you can see the land cover change within 20 years, right, for Las Vegas. So you can see the dramatic increase of urban area during the last 2 decades, and also the changes in the reservoir, the water body, right? And it's not very typical because you already have data. You only need to just to get the data layer, and then you can visualize that easily. Next one is the link maps. So the link map allows you to create multiple layers. And so this one right now, I think it doesn't work well on Google Colab. So let me see here. Yeah, it's supposed to, if you move your mouse on one, you move all of them. It works locally, but right now it doesn't work on Google Colab. So you can skip this one, but at least you can see, you can create multiple rows, multiple columns of maps, and you can see them side by side. So it'll be useful if you need to inspect different bank combinations, and you want to see which bank combination is better for highlighting a certain feature. Then you can use this one to take a look. Again, right now this doesn't work properly on Google Colab. So if you try it locally using your Jupyter Lab, then you should link. So all the maps will be linked together. So if you move one map, you will move all other maps so that you always get the same location. Next one, time series inspector. So this one allows you to, if you visualize data, if you have a time series images, multiple images for the same area, and you want to see them comparing side by side. So there's a function here called TS inspector, and allows you to pass in different image collections. So let's run this one and to see what it looks like. So if you create a map, and then so if you're going to see upper left corner here, you're going to see this drop down list. So what we're doing here is that we load this land cover data. So it's the image collection because it's multiple years: 2001, 4, 2006, 8, 11, 13, 16, 19. So we have 2, 4, 6, 8 time periods images. And so with these two drop-down lists allows you to compare data side by side. Otherwise, you have to add all the data layers to the map. So sometimes it can take some time. But for me here, right, I can just zoom to this location. Again, Las Vegas, right? Then you can compare, for example, 2001 and 2019. So you can see the changes of the area. If on the drop-down list here, if I change the year, it will update the imagery, right? So I can change to maybe 2013. I'm not sure if you can see the images being updated on the fly. I can change to 2006. I can change it to 2008. So it's interactive. So that widget allows you to change the data layer easily. Last one here, the time slider. So time slider, I'm not sure if it works here on Google Colab or not. It's the same thing. It also allows you to visualize time series data. So what we are doing here is we are accessing the MODIS data, NDVI, for the month of June. So because it's daily, so basically we have daily images for the month. So it's going to have 30 images and allows you to visualize those 30 images all at once. Otherwise, you have to add 30 data layers to the map. But we use this time slider so that you can slide through. So if you look at the lower right corner here, there's a button here. So if you change the date, if you drag the slider, you're going to change to a different date, and it's going to load the data layer for that date. So in that way, you can visualize the entire time series. You can also click this button, the play button, but I'm not sure. Yeah, okay, it works. So it's just going to be a little bit laggy because when you are changing the date, it's basically sending a request to Google Sending and then get the images and then pass it back. So it might not work. It might not be very smooth, but you can always use the slider to drag and then find the date that you want, right? So think about you're working at a global scale. You want to look at images for a certain date. You might have hundreds or thousands of images. You want to quickly see them. You don't want to add all the data layer because it'll be overwhelming. But this one allows you to pick what date do you want and then you just visualize instantly. Besides NDVI, for example, I can also visualize weather and climate data. So this one is the temperature. So look at this one here, NOAA temperature, and it's within 24 hours. So every hour you get one imagery. So within 24 hours, and then I can visualize that and then add a time slider. So this one shows you the temperature changes within a day. So it will be daily temperature, hourly temperature. Again, I can change the slider. You will see the temperature dynamics, like changing from, so the red color means high temperature, blue color means lower temperature. So you can change it. You can see that interactively. Again, most of these tools basically just one line of code. So in Google Geemap, you can just use this to load the data very, very easily. And the last one here I'm showing you is the time series data for a certain area. So this one shows you the data covering San Francisco and using the Sentinel-2 surface reflectance and cloud cover is less than 10%. And I don't know how many images in there. It's probably quite a lot, but the image is starting from 2018, so you can scroll through them. Right? You can see all the images, and these are all the high quality images. So if you are working on a resource project that need time series data, need high quality images for a certain area, and you want to see the images first before you downloading the data, before you running analysis, this can be very useful, right? So in here, right, we have data all the way from 2018 to the current, like 2024, just last month. So there are a lot of images in here. I'm not sure how many in there. Let me run this one. Create a new code block. So this collection here is all the time series images covering San Francisco. So what I can do is I can just say collection dot size and then run it. Okay, so 105 images. So that means there are 105 images meet the criteria with cloud coverage less than 10% for San Francisco. And you can visualize them all at once, right? So just like what I'm showing here, you can change it to a certain date. Similarly, you can do it for other area. For example, let me go back to, let's look at the area that we are in here. Where is it? Nashville. Okay, so we're here, and I believe somewhere here, right? We're near this building. So imagine you are interested in doing research for this area. I want to get the images. So imagine how many lines of code you need to write. I already give you the example. The only difference is right now the location changed, the coordinates. Everything else should be the same, right? So all I need to do is to figure out the location. So what you can do, you can just zoom to this area and then you can get the coordinates, see what's the center, because right now my map is centered around this area. So as long as you can get the center, you should be able to do that. Or you can place a marker on the left side here. You place a marker, for example, I want to look at this building. Right? You click that, and after that, I can just simply use map.user ROI, run it. You should be able to see the coordinates. So this is the coordinates of this location. Okay, latitude 36, and then longitude negative 83 something. So I can just copy this one and then go back to my source code. I come back to here, and this one here, this is right now the longitude, right? Oh, I copy the latitude first. So latitude, and then again copy the longitude and paste the longitude here. That's it. So everything else remain the same. But right now, my of course you also need to change it from here because I'm going to center the object. So let me also do it here. Keep in mind this might be confusing. So when you create a map, it's latitude, longitude. But for Google's engine, it's longitude and latitude. So the order is a bit different. But if I run this one right now, it's going to zoom to this location. See here. So now I have all the images cloud free for this area. And I don't need to download it. You get access to all the high quality images. Again, if you want to see how many, I can just do the same thing. Selection, doc size, right? Run it. 169. Okay. So I have access to 169 images for this area. And all I need to do is just use this slider. I can change it. I can switch, move it to a certain date, right? For example, 2022, see? Or even to the latest one. This was December 18. That means it's very cloudy, so not a lot of images during the last couple months because none of them is less than 10% cloud cover. So you see how easy it is. Compare, you go to USGS, you use NASA, US, European Space Agency, and trying to filter the area and then look at it. But you can only look at the thumbnail. You cannot look at the original data. But this one, you can zoom in, you can see the original data. So, and you can also use it for computation, not just for visualization. So it's super powerful. If you need to find data, you need to quickly see the data. This is the fastest way you can see. And you can write algorithm to computation. You can extract base station. You can extract urban area. You can extract all kind of things that you want. And visualization is super easy to do in Google's engine. You're welcome to change to other area, any your hometown, your apartment, your house, anywhere you like. You'll be able to see these images. So I only show you how to do the Sentinel-2. You can use Landsat. You can use USDA name imagery. There are tons of data available in the data catalog that can give you access to those. Okay, any questions? Would you like to work on the exercise or we need to continue? There's a exercise 2 here if you want to work on that. So for example, you can use the lane cover data and then you can use NFCD, also the state boundary. You can create, for example, a slide kind of a map for your selected area of interest. For example, for Tennessee, for Texas, or anywhere you like. So it's going to be very much similar to this one. Let me show you here. If you go back to this example here, right? This is for the entire US, and you have this, but if you want, you can just clip that one to just a certain state, and then you can create this one. So just to focus on an area. So let me show you how to do that, right? You don't need to start seeing from scratch. For all the exercise, you can copy some example and make some changes, and then you will become a new application. So I can just copy this code block and come to this exercise here just to show you how to do it, right? So right now I'm asking you, okay, create a map, and then show the land cover change for Tennessee between 2001 and 2019. And so I just paste this one here, run it, and this one is at the national scale. So what we need to do is actually to clip to Tennessee so that we can make the map focus on Tennessee. So what we want to do is to basically find out how you get to Tennessee. So I show you this one here, the feature collection, this one. The feature collection, this one contains a polygon for the entire US, right? So we can do the filter to get to Tennessee. So what you want to do is basically, you can just double click, or you can just select this one here, copy it, Control C, right? And then I can come back to here. You can define a new variable, for example, state equal to this one. So the entire US state. Then you can get Tennessee. So Tennessee will be TN equal to maybe state dot filter. Okay, that means you want to select by attribute filters, and then inside there you can e dot filter dot eq. Okay, and then you can, I know based on the example that we worked on earlier, there's a name column, right? And then comma, double quotes, Tennessee, Nessee, right? Yeah. So now we have Tennessee, the polygon, and the last step will be here under this one, because for the lane cover, it's for the entire US. So right now we want to clip the area to just to the state of Tennessee. So then you'll be just dot clip to section, and then just passing Tennessee in there. And then you can do the same thing for the other year. Control C, Control V, and hopefully that's it. So just add a little bit more, and look at this. You see, just right now the lane cover is just within Tennessee, right? And so what we do here is basically adding just 2 lines of code, and then just clip. So there's a function called clip to collection. It's a camel case, so you need to lowercase and then uppercase, the 2 T uppercase, C uppercase. And of course you can just zoom to the location. So if you know the state of Tennessee, I can just come here at the end, map.center object, and then just TN. That means you're going to center around Tennessee, so that the map will be centered around Tennessee. And run this one again. Right. So right now the zoom level, if it's not enough, you can change the zoom level. But how about this? Zoom equal to maybe 6 or 5. 5 is too small. Probably 7. Okay, yeah, looks pretty good. So, and then you can use this slider. See here. You might need to zoom in a little bit to see the changes. Like all the lane cover. You can see some changes in here, different color. Okay. And how many lines of code? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 lines of code. And you can easily customize this one for anywhere, any state. Because all you need to do is just change 1 line of code. So here, if you want to do, for example, they say I want to change it to Alabama, right? I want to change to California. All you need is just Alabama, right? And run it. I don't need to change anything else. It should be pretty automatic. See, now I have this for Alabama. So it's up to you what you want to do. And this makes it really, really powerful, because It doesn't matter what area you're working on. The more important thing is like you figure out your workflow, and then you can easily transfer that to other area. You can work on Alabama, you can work on Alaska or Arkansas, or anywhere you like. It doesn't matter. And you only change one small thing. Everything else remain the same. And this right now, so far, we're only doing the visualization. We haven't really done any analysis yet. You can also run, for example, what's the lane cover type in this area? What's the dominant lane cover type in Alabama? What's the top 3 lane cover types in Alabama? And what's the percentage of those lane cover types, right? You can run the computation very, very easily just with one line of code. So feel free to customize, use the example, and then to change to some other area. You don't need to use the NLCD. You can also use any other lane cover type. But this give you some of those flexibility that you can use any data you want. You can run any computation you want, and you can visualize the data easily. Okay, so that's about the data visualization part, and I think we've covered the first 2 sections. And we can take a 10 minutes break. So 3:15, we come back at 3:25. And then we can continue to do some real analytics, how we can really run large scale computation and then get the result very, very quickly. Okay, so I will see you later. Okay, this continue. Let me go on the microphone. In the next section, we're going to talk about how to do some analysis. So far we cover how to get the data, how to visualize the data, how to filter the data. And once you have the data, you might want to do some computation. So this is where the real power of using cloud computing is. It allows you to run scalable computation. It doesn't matter how big is the area, how many images, the process is pretty much the same, but you can get the result very, very quickly. So in the next example, I'm going to show you how you can get some attribute and then you can start doing some analysis. So before you get into that, I want to show you some of the tools. For example, here, create a map, and then let's look at this example. Once you get the images, sometimes you might want to get some metadata. So this is a landscape imagery covering the California, and we filter the data to this based on the coordinates, and we get the first imagery. After that, you can, for example, get the property name. So this can be useful if you need to figure out the metadata. For example, what's the cloud cover? What's the quality? So those metadata is coming from the sensor itself. And the property name shows you all the attributes. So basically the metadata, and you can use the doc dictionary to see the property value and also the property. So this one shows you, for example, the cloud cover, right? It shows you the landscape imagery that we are using, or what's the cloud cover is 5%. Lane cover, cloud cover on the lane area is 6%, and there are a lot of information in here. So sometimes if you need to see some metadata before you do analysis, you can do it like this way. You can also get the cloud cover specifically. So image.get and then double quotes basically mean the property. So you get the property value for that property for that image. You can also use the image prop all at once so that you can get all the properties. It's going to return as an Earth engine object. You can also do it like this. So you can show you, for example, what's the date, right? So this is the date for the imagery. And you can also see, for example, the nominal scale, the pixel resolution, 30-meter resolution, the pass and roll, and also some other information in here. So it's up to you what you want to get. And the lastly is about the statistics. So sometimes you might want to get some simple summary statistics of imagery. So we're using, for example, calculating the minimum, the maximum, the mean, the standard deviation, the sum, or something like that. So we have this landscape imagery. It has multi-spectral bands. So for each band, you're going to have minimum, maximum, standard deviation, so those things you can quickly, just to get a basic idea about what's the value range of the imagery for different bands. So this give you just one line of code. You can quickly run the analysis and get the result easily. So that's the basic, so-called the basic descriptive statistics of an imagery. And next example, I want to show you how to do some zonal statistics. So let's load some data first. And this example, we have some data, the US state boundary, and also we have the data, the DM data at a global scale. We also have a landscape data layer, although it's not showing up in here because we hide the data layer, but you can turn it on if you want to. Right, so we have 3 data layers. And so the zonal statistics is basically you want to do the statistics based on different regions, different groups. And by looking at this example, right now, if I ask you, which US state do you think has the highest mean elevation? Which US state has the highest mean elevation? By looking at the map here. Which one? Colorado? Yeah, you see this all the white color, right? Because the white color means higher elevation. So it's pretty odd, maybe quite obvious. Colorado has a lot of high mountains in here. And if I ask you which US state has the lowest mean elevation? Lowest. Louisiana? Yes, any other guesses? What else? It's hard to tell, right? Because it's all green color. It's not easy to, you can guess. This is where you can use analysis to find out exactly which states. And so what we can do here, you see this one line of code. Look at this one, zonal statistics. So you can pass in the DM, and you can pass in the vector data, basically the state boundary, and the output is, we're going to save the output as a CSV. And the statistical type, we're going to calculate the mean. So the mean means we're going to, basically for each state, we're going to calculate the mean elevation within each state. So each state, you're going to have a value for that. And this is where you can find out which one has the highest, which one has the lowest. Also the scale. By default, the DM, this one is 30-meter resolution. You may want to run it in 30 meter if you want to be very detailed, higher scale, very fine scale, but sometimes you will run out of memory. So for this case, we don't really need like 30 meter. I mean, you can resample is 1,000, basically 1 kilometer. And let's take a look how fast, how long does it take? Seconds. Within seconds, you get the images. And once you get images, now we can start looking at the data. So you can either go to this one here, you will see this CSV, you can open it, and so it's going to look like this. So this mean column here, so this one is the elevation, right? Mean elevation. So look at this one, which one is the highest, right? Okay. Is it missing something? Obtain rows. Let me use this one. I think just use the source code will be better. So basically, we're reading the CSV as a data frame, and then you can look at it. Ascending equals. Okay, so ascending equal to 2 means we are from the lowest to the highest. Okay, so the mean elevation, the lowest one is which one? Delaware. Okay. It's also in the coast, right? It's only 13 meter. Mean elevation is only 13 meter. And then the Mariana Islands, Virgin Island, Florida. Yeah, Louisiana is number 6. It's close. But you can also descending. So you'll be fourth. Then you'll be descending. So descending, so we can look at what's the top, the highest mean elevation. In this case, yeah, it's Colorado. Okay, the state. 2,095 meters average mean elevation. Second one is Wyoming, Utah. New Mexico, right? So this is how you can actually use the statistics to find out. You don't have to guess. I can give you the concrete answer and give you the number. And this is where it's just using the zonal states function, just one line of code. So give me the image, give me the vector, and I can calculate whatever statistic you want to calculate. It can be mean, it can be maximum, it can be, or I can, for example, here I can calculate the standard deviation. It will be STD, for example. So what does this really mean? So standard deviation basically means within elevation. So basically you can, if you're trying to figure out which US state is very flat, or which US state the terrain is very up and down, very rocky, right? So if you want to use that, you can use the standard deviation, then you can run the analysis. And this might take a couple seconds or 10, 20 seconds, but still much faster than you have to download the data and then you need to run the computation using your desktop computing. It's going to take a while. And these are doing basically in the cloud and using the parallel computing. The reason that earlier when I did the mean, it was much faster because I ran the call yesterday. So Google actually stores some of the cache. So it doesn't run like all the time. Some of the results are being cached there. So when you run again, it will be very quick. But this one still, you see, probably 10, 15 seconds, we get the result. If I run again, you'll be much faster. But if you run it a couple days later, then you will redo it again because it doesn't store the result permanently. And similarly, once you have this, now we can see the images, see the DM here, right? Now it's called STD DEV, right? And similarly, you can sort the results. Or we can write the code, right? STD DEV in here, STD DEV, right? And we can see which US state, for example, the terrain is very flat. Basically, there's no much standard deviation, no much variance. So if I scroll down up in here, Hawaii, okay, the terrain in Hawaii is the most up and down. So different, very different. And the lowest one is also Delaware. So that means it's very flat. There's not much variation in terms of terrain. And also Florida, DC. Anyway, so loads of things you can think about. What kind of question? So it doesn't have to be DM. It can be temperature, for example. You want to calculate, for example, during the summer, which US state has the highest mean temperature? You can do the same thing, right? If it's just one image and give me the polygon, then you can do the statistics. It can also be rainfall, for example. What's the total rainfall for each state, for each county, for each country? It doesn't matter. It can be basically just one image, one vector, and then you can do the statistics between those data sets. Next one is doing the zonal statistics of multi-spectral bands. For the DM, we only have one band, but sometimes you might have a time series. For example, you have temperature, you have Landsat data, for example, and allows you also to do statistics. So this one, we can do the same thing. We get the Landsat data, we get the US states, and we're going to calculate the statistics, and the output going to it as a CSV. And run this one again, take a look. So now we have, if you scroll up, right, we have B1, 2, 3, 4, 5, 6, 7. So you have 7 spectral bands. So what this one is doing is calculating the average value of each band for every state, right? So individually, so you can get something like this. Again, like I said, it doesn't have to be Landsat. You can also do temperature, for example. If you're trying to figure out what's the trend, right? You're trying to study the temperature dynamics for a certain state or county level or sensor level, whatever. You can have the time series as a collection, and then you can pass the images to do the zonal statistics. Then you want to get the temperature, for example. Okay, yesterday in Tennessee, the temperature was 20, and today was 25, 23, right? You can see the trend. So this can help you get it all at once for every state. So basically for every polygon, it can be county level. You're trying to see, imagine you have data for all the counties in Tennessee, and you try to figure out which county has the largest increase of temperature during the last year. You can have 65 images, and you can calculate the statistics and it can show the trend. So basically, have a table, something like this, and then you can use that to do some additional analysis. So the zonal statistics can be applied to just a single band, or it can be multi-band, and it can be hundreds of bands, depending on how big is your data. Questions? Next one, zonal statistics by group. Okay, so the early example, we use the zonal statistics. So all the data is basically continuous data. So DM like have a range of values. But in this case, I'm going to show you a different example. Here we have the NLCD, National Land Cover Database. And we also have the US state boundary. So my question is, which US state has the largest agricultural area? Which US state has the largest agricultural area? If you look at the map. So which one is the agriculture? Right, number 82. This brown is color here. But look at the map, right? So if you work for the USDA, imagine you work for the USDA, you need to know, like, okay, you need to do some investment in some states, right? You're trying to see which state has least agricultural area, trying to increase, or you're trying to do some investment based on agricultural area. You certainly need some analysis to run and to get the result. So right now you give it a state polygon and also give the land cover, and if you have to guess which one has the largest agricultural area. Or you can ask the other question, which US state has the largest forest cover? Which one is the largest grassland? Right. So in this question is no longer just aggregating all the pixel values within the state, because this land cover, so it has unique values, so it's categorical data, right? Because each state you want to have land agriculture, you want to have forest, you have urban. So how do you figure out? Because you're going to have multiple categories. Again, one line of code. So you can just use the zonal statistics by group, passing the land cover, passing the polygon, and what's the output? And the statistical type, here we use the sum. The sum means you're going to count all the pixels belong to the same category. And then you're going to calculate, basically calculate the land cover area, each land cover type in each state. And let's take a look. Just run it. It should be a couple seconds. Then you should be able to get the result. So this is the 30-meter resolution data. It's a pretty big image. It's maybe 50, 60 gigabyte imagery. And you're going to do under computation. And you'll be able to get the result within roughly 10, 15 seconds. Okay, it's done. And after that, we can just load it as the table. So take a look at this. So now we have this table, and this table shows you the attribute for the original vector data, but it also has land cover class. Okay, class 81, 71, 82. It's not alphabetically, but you will see here, this is the total area. And also, earlier when I said this one, decimal place a denominator, a million. So basically means converting the unit from square meter to square kilometer. So what this number showing here, this shows you the class is basically the land cover type, square kilometer. And so if you want to figure out, for example, which land cover type, which state has the largest land cover type, you can just do the sorting. So for example, if you go back to this one, we know the agriculture is 82. So agriculture is 82. So what you can do is come to here. You can sort the column. You'll be just dot sort. Any sort values. And then you can just pass in the column. So for example, class 82. Okay. So what we're doing here is to sort class 82. And by default, it's going to be ascending. And you can scroll all the way to the bottom. You can see which one has the, which one is 82. So it's somewhere here. What's this one? Iowa. So Iowa has the largest agricultural area. If you go back to the map, it probably makes sense because it has the largest brownish color somewhere here. Right? It's almost all agriculture. But you can also do the I think you can do ascending. It is TNT equal to false. Run again. So scroll up in here. All right, so 82. So this one has 107,000 square kilometer. So it's pretty big. And then compared to the second one here, this one is I believe Kansas. Yeah, North Dakota and something like that. You can change it to other type. For example, if you're looking at forest land cover, you're trying to see which US state has the largest evergreen forest area. So this one will be number 42, right? So it'll be class 42. So I can come back to here and just run this one, 42. Execute it. And scroll up. So which one? Number 42 here, 88,000. Top one is Oregon. So Oregon has the largest evergreen forest, and then Montana, California. So again, you can come back to the map to check, right? You need those dark green color. So Oregon here, yeah, it's pretty big one. And you do the same thing. You can do water. You can do urban. You can do grassland. It doesn't matter. So you can do any land cover type you want. So this is so-called zonal statistics by group. It's good for this kind of category, especially for land cover type, or it can be any categorical data. For example, high, median, whatever. You're gonna have the value 0, 1, 2, 3, 4, 5, something like that. So you can use this just one line of code to do the calculation. So the example that I just show you, use the sum, basically calculate all the pixels and get the area. But you can also do the percentage. So the question that we can ask is, which US state has the largest agricultural area compared to its state area? Basically, the percentage, basically agricultural area divided by the state area. So if you're looking at, for example, right now, maybe Iowa here, maybe, yeah, agriculture probably account for, I guess, 70-80%. If you find the other states, might be, for example, this might be 30-40%. But it doesn't mean you have the largest absolute area, you're going to have the largest percentage. It's not always the case. You might have a smaller state and have a much smaller agricultural area, but when you divide it, it's going to have a large percentage, right? So in this case, you can use the percentage. So this is where the last example here showing you the state type. Use the percentage. So the percentage means you get the total area of the land cover type divided by the state area, and then you can get the percentage. So if you run this one, and let's see what the results. It's probably going to be pretty close if you look at the agriculture. But for other land cover type, it's hard to say. Hard to tell which one is like higher or lower. For example, if I ask you which US state has the largest forest cover compared to its state area. And we can do the same thing. We can run the result and then you can get all the statistics. So compared to the early example, like this one, you will see all the numbers ranging from 0 to 1. Basically the percentage. So what this one is showing here, for example, if you scroll to the bottom somewhere in here, right? So this, if you add them all up together, it will be equal to 1. So you can figure out, for example, in each state, what's the percentage is forest cover, what's the percentage of basically the land cover composition. And in total, it'll be 100%, right? And then you can get the percentage of each land cover within the area. So that's the zonal statistics by group. The last zonal statistics is zonal statistics by between two images. So this is another example here. Let me show you. Okay, so we have two data layers, and we have one land cover, and the other one is the elevation. Okay, so look at this. We have the elevation, we have land cover. right? So right now we're not dealing with polygon anymore. But what kind of question we can ask, like for these two images, right? So this is also very common in GS. So we have lane cover, we have a DM, and maybe I can ask you, for example, which lane cover has the highest mean elevation? Which lane cover type has the highest mean elevation? Which one? Say it again, I could not hear. No. Right now we're not dealing with location. I'm talking about lane cover type and DM. So which lane cover type has the highest elevation, mean elevation, for example? Which one? Grass lane? Right, we have different lane cover type in here. So look at it. So what I know, for example, which lane cover type is like a high altitude at the high altitude area? Right. So in this way, we're not dealing with polygon. Right now, we're dealing with two raster, right? So we have category data. We also have the continuous the DM. So this one, we're going to use the zonal statistics by zone, basically having two images. And you can give me a DM, you can give me the categorical data. So this is lane cover, and then we can run the statistics, and then you can figure it out. So the mean elevation, so look at this. Very quick. Show you for different zone, different group, different lane cover type, and the statistics. This one is the mean, the elevation, the mean elevation. So look at this table. Which one is the highest? Number 12, right? So what is number 12? Perennial ice and snow. Why? Because it's probably most in at the top of the mountains. And it does make sense. So if you go to, for example, some of this area, you're probably going to see some of those snow and ice somewhere. Maybe here. Yeah, it's probably hard to see, but you can certainly see some of those light color stuff at the top of the mountain. Because if you turn the data layer off, if you have the satellite imagery, you'll be able to see it. So let me turn this one off and change it to an imagery. Right, somewhere here, something like this. Right. Yeah, some of these things. So it's a very small area, so it's very hard to see, but this is something you can do if you're dealing with two images, one categorical, one continuous. Then you can use this to get the statistics. And you can also do the sorting if you want to. You can also do the standard deviation. Like I said, if you're trying to figure out, for example, which lane cover is like distributed everywhere, high elevation, low elevation. So basically the standard deviation is very, very high. And if you look at this one, which one? You can do the sorting again if you want to, but it's not too many, so I can just look at the numbers. So it'll be this one, right? 969. So that means the variation changed a lot. And it's number 42. So what's number 42? Evergreen forest. Okay. So that means the evergreen forest, the elevation is some like very high, some very low. So you basically distribute everywhere. All right. So that's about some of the simple zonal statistics that you can do to do analysis based on one image, one vector, or you can have two images. So it has a lot of applications. So this exercise here also shows you, like, for example, how to do temperature. So you can get the temperature images for a specific date, a specific time period, and then you can try to figure out, well, okay, what state, for example, has the highest mean temperature, which state is the hottest or you can also look at the time series of images, and you can figure out hot spot of the temperature or cold spot of the temperature. So I'm going to keep this exercise in here. You can do that after the workshop. We still have 2 more sections to cover, but I encourage you to look at the example and see if you can figure it out how to do that. All you need to just use some of the example code that are provided for others, and then just replace the data, and the workflow pretty much the same. You give one imagery, you get one vector data, and then just do some zonal statistics. So that's about the zonal statistics. And the next one, I'm going to show you how to use the I'm going to skip the other 2 sections, creating the coding grid. We can quickly run through it if you want to. So let's quickly. So this section allows you to create coordinate grid, and this can be useful if you're trying to do some longitude, latitude, or changes by longitude or by latitude. So for example, you're trying to analyze the temperature changes by latitude, then you can create this latitude grid, and you have the imagery. You can do under zonal statistics. Then you will see the aggregation. For example, the temperature within each latitude grid or longitude grid. And this one just create the vector data. It doesn't really do the analysis, but you can if you want to, right? So this one is by longitude. So you can create longitude every 5 degree, every 10 degree. It's up to you how you want to do that. You can also create basically a fishnet. For example, 10 by 10 degree, something like that. You want to create something like this. And this can be useful. You're trying to do analysis, for example, block by block. Or you're trying to export the data later. If you're doing exporting data for large area, it's going to take a while. But you can create something like this to export data small piece by small piece. And the fishnet is pretty much the same thing. You can create a grid of based on an existing polygon. You can subdivide the polygon into smaller pieces, and then you can do analysis one by one. So look at this. So we have a polygon. We're going to subdivide it into smaller pieces, smaller tiles. And then you can use that to do zonal statistics, because eventually zonal statistics is giving you a polygon, a bunch of polygons. So you can create polygons like this easily. Again, you can try it out. We don't have time to get into the details. So the next one I'm going to show you is doing some lane cover analysis. So imagine that you already have some, let's say, forest data. You want to see the forest loss or the forest gain in a certain area. Google is sending already some existing data. So this one I'm using is called the Hansen Global Forest Cover Data. You can click the link to look at the information. So essentially, it is an image that with multiple bands, and they have tree cover for 2000, and also they have forest loss, forest gain, and also which year it was lost, and also shows you, for example, spectral bands. Okay, the first year and the last year. So this is the dataset covers from 2000 to 2023. So with 23 years difference. And so first, let's look at the data, what it looks like. So we're going to click here just to show you what the data looks like for the imagery for 2000, and also the imagery for 2003. And so we have 3 data layers in here. The last data layer is the tree cover. So tree cover is measured in percentage from 0% to 100%. And this is the original data. So this is Lancet 2000. And this is Lancet, I believe this is 2003, no, 2020, because it's updated. Anyway, so you can think about, you have the first imagery, you have the last year of imagery, and we also have the tree cover in 2000. So if you look at this one, and then if you zoom in to the US, somewhere here, for example, right? So the tree cover, the value range from 0 to 100%. Basically, within each pixel, what's the forest cover area? And you can change this opacity here, right? So this tree cover that I'm showing you here is delineated based on this imagery, Lancet 2000. you see it's pretty close, right? So ranging from 0 to 100%. And the convention is that if the pixel has more than 10% for tree cover, you can treat it as a forest pixel or a tree pixel. So we are doing a binary, a threshold. So this one shows you the tree. If it's greater than 10, we're gonna extract the value, the area, and then we're gonna make it as green color. So right now, if I run this one, you see we basically change the imagery from 0 to 100% to a binary. So if anything greater than 10%, we extract that. So now if you see this one, right? So the green area, right now this is the forest cover. So we can highlight it. If you think it's too much, you can change it to, you can change the threshold to a higher value. For example, 20 or something like that, but we can just use the 10%. It's the default one. And so what this one showing here, this is global forest cover. So I give you an imagery of the in 2000, give you another imagery in 22 or 2023, and I also give you the forest cover in 2000. And now I'm trying to figure out what's the forest cover right now in this year, because there's another data layer that shows you whether it's forest loss or forest gain during the last 2 decades. So here, there's visualize the forest loss. Okay, so if you run this code block, it's going to show you the forest loss, and the loss here. There's also a color bar at the low right in there. So the value range from 0 to 23. So if it is 0, that means it's not lost. If it is 1, that means the forest was lost in 2001. So the baseline is year 2000. Okay, and we have 23 years. So if the pixel value is 10, that means the forest was lost in 2010. Okay. If it is 20, that means it was lost in 2020. If it is 23, that means it lost in 2023. So if you see from this color bar in here, from yellow to red. So yellow means the forest was lost in the earlier years. Red color means was more recent. So the forest was lost in recent years. So of course, if you zoom in, you can see some of these forest loss. And again, this is just a data set just for demonstration. It doesn't mean that it's super accurate. If you zoom into an area, sometimes if you zoom in, you will see there's lots of errors or artifacts. But you can zoom in and then take a look at the data, and you can turn the layer on and off to see if it makes sense or not. And some of those basically maybe already recovered, but some of those might be real. For example, if you zoom to maybe some deforestation area, for example, in the Amazon, for example, right? So if you zoom in, something like this, and if you turn the layer on and off, yeah, you do see there are a lot of changes in this area. For example, here, right? Some of the cloud, and some might be lost, some might be not. But this is what the data shows you, and it shows you every pixel at the global scale when the forest was lost during the last the last 23 years. You can also see the forest gain. For example, you can have a forest gain in yellow color and a forest loss in red color. So in this case, you can see where's the gain, the forest gain in a certain area. So there always be loss and lost some gain during the last 2 decades. And with this data set, now we can start doing some calculations. So we can figure out, for example, which US state or which countries has the largest forest area, which country has lost the most forest, or which country has gained the most forest, right? So those are things you might be wondering if you're doing some forestry analysis. So now let's start doing analysis. So we are going to use the country dataset. So first we can load the country dataset, basically the country boundaries. And then we can start doing the same zonal statistics, right? Because earlier I showed you how to do the land cover, how to figure out the land cover, but this is the same idea. I give you the polygon, I give you another raster data layer with forest cover or forest loss, whatever, and then you can calculate the total within each country. So first one, we're going to do the zonal statistics by country and calculate the sum and get a forest cover. So this one answers the question of which country has the largest forest area. And if you don't know, let's run it and then we'll take a look. And we can also create a pie chart. Okay, so just one line of code, take a look. It's going to show you at the global scale which country, okay, Russia has the most forest, 26.9% of total, basically the global forest area, Russia has the most, 26%. And then other means all other countries. Canada has second, Brazil, US, China, so the top 5 countries has a lot of forest in here. This is just one line of code based on the zonal statistics, right? So the zonal statistics, we calculate the sum, the total forest area, and then we just use, based on the CSV, we create this pie chart. You can also create a bar chart, something like this, right? So it can show you, and this is interactive, so you can actually zoom in and zoom out to see it. And if you click this one, it's going to go back to the original one. So this shows you basically clearly what's the top 5 countries that has the largest forest area. Besides calculating the total sum of the forest area, you can also calculate the forest loss, because we already generate the data layer for the forest loss, right? So we can figure out during the last 2 decades, which country has lost the most forest, or which country has gained the most forest. So the same thing, we are using the zonal statistics, but this time we're using the tree loss, okay? So the tree loss is a binary image, yes and no. And then you can calculate the sum, and after that you can do the same thing. So here, right? So this one shows you the forest loss, all the forest loss during the last 23 years. And again, which country has lost the most? Russia, Canada, Brazil, US, Indonesia, something like this. So you can get some analysis really quickly, and you can also create a bar chart to look at it, right? So those are some of the common applications. When you're doing land use, land cover analysis, you always want to use this kind of zonal statistics to quickly get an idea how much has changed, or which country has lost most, or which country has gained most, right? So if you're someone doing some investment, or if you're government agencies, you're trying to see if some situation has improved or not, right? Or you can try to, is that you have invested a lot of money for forest or agriculture, or whatever. You want to see that it's growing, it's increasing. So with these data images and with this data, you can get the answer very quickly. And it doesn't matter how big is the area, you can do that pretty quick. And next, another exercise. So for example, earlier we saw it at the country scale. Which country has the largest forest area? Which country has lost the most forest area? But right now I'm changing the scale to US states, right? Earlier, the US is treated as one single country. But now I'm asking you, for example, which US state has the largest forest cover? Or which US state has lost most forest cover? Which US state has gained the most forest, right? So all we need to do is just change the country from country to US state boundaries. Everything else remains the same. All the source code, you can just run through it. You'll be able to get the result easily. And it can be temperature, it can be agriculture, it can be water, it can be urban, it can be anything, right? So basically just one imagery, one vector, and then just run the zonal statistics. Questions? Okay, we're almost there. So we have 2 more sections. The next one is to export data. And then last section is about creating animation. So export data is from outside from Google Search Engine is not as fast as you think. Okay, so it's kind of like you are watching a movie on Netflix, and you think the movie is really cool. You want to keep a copy. You want high definition. It's going to take a while. Okay, and even if it allows it, it depends on internet speed. Google Sensing is the same thing. You can run computation, you can see things, but if you're trying to get the data out and it's big data set, it's going to take some time. But there are different ways you can export the data. So I'm going to show you multiple ways how you can get the data out. The first example, I'm going to load this landscape imagery in here, right? So this is one landscape scene covering California. And you can export the entire image or you can export just a small subset. So for this one, I'm going to execute this one. I'm going to add a small, for example, a polygon within this area. Imagine that, okay, I want the data for this area. I have this imagery, I have this region. Then I can just use one line of code. So this one here, export image, is to give the image, give the output, and also tell me the scale, and then also the region. Then you'll be able to export this one directly to your computer. So Google Sensing allows you to export data direct to the computer. If the imagery is pretty tiny, it's less than 32 megabyte, then you can export it directly. But sometimes if you are exporting multiple images and then the pixel doesn't line up together, you can use this set the coordinates and transformation. So basically, if you're exporting multiple images, you want to make sure that they align pixel by pixel. You might need to specify the resolution, the coordinate, and also the coordinate system. And if your image is too big, it exceeds the limitation, then you need to export to Google Drive. So Google Drive has a larger amount of quota, so you can export large data. But this is going to take some time. It's not instant. So you need to check your Earth Engine code editor to see whether it's finished or not. So for example, after I execute this one, it looks like it's done. It doesn't do anything. It's not finished yet. It's just sending the task to Google Sensing, and then it's going to execute. So I can quickly show you here. It's actually under Earth Engine. So you need to log into the Earth Engine account to see it, and then go to the code editor. And then on the right here, the task. So you see, right now it's actually exporting. So it's showing the progress in here. It's not finished yet. So it's just sending the task. Once it's done, the file is going to show up in your Google Drive. So that's exporting one image. You can also export a bunch of images. So image collection. So for example, this is an example. We have the USDA name imagery, 1 meter resolution, covering a certain area. So in this case, we have 7 images. You can also use this function to export images all at once. Export image collection. And just run this one. We want to output and also the scale. And just run it. You see, it's going to output all the images all at once. So it doesn't matter how many images you have. It can be 10, it can be 100, it can be 1000. You can just use one line of code to export over all the images. So if you're working on a specific area and you get all the time series for an area, and then you can use this to run to export all the data all at once. So similarly, you can also export to Google Drive. Again, you can run this one. It's going to send the task and going to show you how many images. Then you need to go back to the Earth Engine code editor here to see the task. It might take a couple seconds for it to show up. But you see right now we have 7 images showing up in here. It's a task. So you're going to export them one by one. So that's for exporting a bunch of images. And the last one is exporting vector data. So you might be, once you do the computation, sometimes you might do export some vector data out of Google Sensing. So for example, this is the Tennessee state boundary. And you might be doing computation and you might get some result in the feature collection, in the format of feature collection. So here you can export the data to different ways. You can export the data directly local to the local computer. So you can convert the vector data Google Sensing to shape file. And one line of code, see, now I have this Tennessee shape file to my local computer. You can also export as GeoJSON, GeoPackage, CSV. If you just need the attribute table, you can export as a CSV. And then you can also export as a geodata frame, or you can export as a data frame. So it's up to you how you want to do that. So Google Sensing allows you to export raster data, vector data, whatever data you want. But if your vector data is pretty big, it's going to take some time. So try to do all the computation in Google Search Engine and then just export a small summary of the data rather than the entire huge data set. Okay, so that's about the exporting data. And the last section we're going to quickly go through is creating animation. So this is probably the funniest part that allows you to see changes, allows you to create animations, allow you to access cloud computing to quickly do this. Without the cloud computing, this used to take hours, days to just to create a simple animation. But now things can be done within 20, 30 seconds. So what I'm going to show you here is to create, first create a time series. So if you're someone working on an area, you need a time series. For example, every year, every quarter, every month, every week, you can use this function to create it. So I'm going to show you how to use, for example, Sentinel-2, and I'm going to specify the area and also the date range from 2016 to 2022. Then I can just use this one line of code, create time series, and then just give me the image collection. And so, for example, this has 6 years, and then give me the reason and also tell me what's the frequency. Do you want to get an imagery every year, every quarter, every month, and how do you want to create it? So I'm going to get annual imagery, and I'm going to use the median filter. So in this, we have 7 years, and take a look. So what we're doing here is we are getting the images for example, for San Francisco, and this is annual imagery from 2016. And take a look. You can change this 2016, 2017, 18, 19, 2022. So you can create this kind of composite easily for any location, for any area. It doesn't have to be Tennessee. It can be San Francisco. It can be any area, any cities you want. And all you need is just one line of code in here. Just specify the image collection you want and the start and end date, the region. So basically give me the start and the end, and I will process the images at a certain interval, by year, by month, by quarter, something like that. So this one is useful if you need the original data. So this one is the original data. So you can zoom in, you can see the high resolution of the imagery. But it's being processed to create those time series. But if you don't need the original data, you just want to see a small animation, then we're going to create the time lapse. So here, let me show you. We can have different time lapse. We can have basically all kinds of data. So what you need to do, just simply run through these examples, and then you will see what we are doing here. So for example, we can create high resolution time series for a certain area. For this one is using the USDA time series. And you can also create a time lapse. So after you create the time series, then this is original data. Look at this one, right? So it's very high resolution. This is 1 meter resolution, super high resolution. And you can create the animation, something like this. Just one line of code. So just give me an area and tell me how you want it to look. Then just one line of code right here, right? ROI, basically the region of interest. And it's going to output as a GF animation. You can also show you what band do you want to use, right? Near infrared, red, and green, but you can use RGB. So this one can clearly show you, for example, the changes, right? You can see some of those wetlands, right? In the wet year, in dry year, you can see how it's merging, how it's splitting. And besides using basically you can use any satellite data, any time series. So the next one here shows you the Lancet. Right, you can create a map and then you can draw a rectangle. If you don't draw any rectangle, you will just use the default area. So for example, you might be interested in this area, just run this one, and then Lancet time lapse. So this one allows you to create animation for 4 decades, since 1984. And you can do it by year, you can do it by month, you can do it by quarter. You can also change the band combination. So here we are using the short infrared, near infrared, and also red band. And then you can easily create the animation within 30 seconds. So you're going to process all the images for that area, and for every year you're going to process and remove the cloud, and then create a cloud free imagery, and then put them all together and take a look. So within 20-30 seconds, you will have this kind of animation. So you can use to showcase changes on the Earth surface for any area, for any reason, for any bank combination, and it's much better than just showing a static imagery, right? And this is by year. You can also do by quarter. If something changed very quickly, you can also show it by months if you want to. And the nice thing about this, you can change the bank combination. It doesn't have to look like this. You can customize RGB bank combination here because we have 7 bands that you can switch. And you can also change how fast you want it to be, right? So it can be 5 seconds, 5 frames per second. You can 10, you'll be faster. The smaller the number, the slower. You also have a color bar, the status bar at the bottom here, show you the changes. And there are a couple more examples in here. So this one is Las Vegas. So you want to see the length, urban growth for a certain area, you can also do that. So essentially everything is just one line of code, Landsat Timelapse. Just give me an area, and then you'll be able to create the animation easily. And so this one combines all the Landsat data. Landsat 5, Landsat 7, Landsat 8, and 9. So four sensors all together, and combine them. So for each area, we are processing a lot of images, hundreds of images. And if you have to do this like manually, it's going to take you many hours to do that, because you have to go to USGS, you need to filter the data, you need to download them, and then you need to combine them like by year, and then do that for all the years. So this looks like 20-30 seconds, but it's super fast compared to do it in the manual way. Like I said, you can do that for any location. It doesn't have to be in this area. So you can clearly see the urban expansion in the Las Vegas. And the last example here shows you, for example, this is in Hong Kong, for example. And if you don't like coding, you can also just create a map, and then you can, without coding, you can also create animation. So this one finished, and then I'll show you how to do that, create animations without coding, right? You can go to any location around the globe, and then you can just simply create animation for anywhere, any area that you like. So maybe let me go here, for example. Let's find look at the area of this forest, the state forest. So for example, where is it? Okay, let me look at this one first. So Hong Kong, okay, Hong Kong airport. So you can see the construction, how it's developing during the last couple decades. So next one, let me show you how to do it without coding, right? So when you create a map, and they say I want to look at this area, so I'm going to go to Nashville here, and where's the state forest here? Where is it? Okay, here, right? So right now we're somewhere, I believe somewhere here. So imagine that, okay, you want to see the changes in this area. You just create a map, and then there's a button here, upper right corner. Click this button, and the first row, the third column, if you click this one, I'm going to show you the Basemap in here. So all you need to do is just simply draw a rectangle somewhere in here. If there's not much changes, probably it's going to be very difficult to see, but you can then just create time lapse. You'll be able to create an animation. So under the hood is going to process all the images from 1984 to the current date, and then it's going to show you the animation by year. And right now it's doing the computing. It's going to take usually 20-30 seconds. Then you have the animation, but you can use the showcase changes anywhere. If you see any development and something that can be captured by the satellite data, you'll be able to use this way to basically no coding, just create a map and then just navigate, and then just select some options. And here allows you to change the combination of everything in here. They have different bank combination that allows you to change. Is it coming up? It's supposed to be loading up on the map. It is not that. Let me click here, download the imagery, and download it to my computer, and then I can open it up. Okay. Right now, this one doesn't. My Mac computer doesn't show you the animation, but this is the resolution is pretty low, so it doesn't show you the details. But you can look at a larger area, or you can use the USDA NAP imagery high resolution to show you the changes. Okay, so this about the lane set. You can also do Sentinel-2. I will show you the MODIS. Okay, MODIS is like large area, large scale. So, for example, I can look at the MODIS changes for Africa, for the entire continent. And again, under the hood is processing a lot of data because it's getting the data for 20, 30 years, and then it's doing the aggregation by year. And take a look. No, doesn't take too much time, but you can see this kind of a dynamics very, very easily. So you can clearly see how the phenology changes throughout the season at the continental scale. And without cloud computing, this can take you a lot of time to process because you need to download all the images for 20, 30 years. And then you need to basically do the aggregation. It's going to take you hours, but now it can be done in seconds. So you can also do temperature. So if you're interested in studying temperature, I can create imagery of ocean temperature dynamics. So you can see how the temperature is changing throughout latitude, throughout the year at different seasons. So lane set is for capturing urban lane use lane cover change. Mode is more like for large scale because the resolution is relatively coarse. And you only get imagery, for example, daily or weekly. But if you need to monitor some events that happen very quickly, we also have high temporal frequency data. Okay, so this one shows you the ocean temperature dynamics throughout the years. And you can have this one here, upper left corner here shows you the date and the months. And the lower right here shows you the color bar. So this can be useful if you're studying ocean temperature and if you want to create something like this. You can use the source code easily. The last couple examples shows you how to create animations using the GHOST data satellite. So the GHOST satellite was the one launched by NOAA. It's for weather and climate. So this one has high temporal frequency. Every couple minutes you get one imagery. Compared to Landsat, you only get one imagery every 2 weeks. So this one you can get minutes imagery every couple minutes. So if you want to monitor, for example, forest fire, volcanoes, eruptions, hurricanes, something like that, you can use this. So this one, for example, right? Look at the Tonga volcanic eruptions in 2022. Every 5 minutes, so you get one imagery. And look at how easy it is, right? So specify the area of interest and specify the date, then just one line of code. So you're going to grab all the images together and then just create this animation for you. So this is something that you may see on the social media. Like next time if they have, this is just for the volcanoes, but you can also do, for example, hurricanes. It's the same thing. So all you need to do is figure out what's the area you want to focus on, what's the time period for the event, and then you can use call this function, one line of code. Then you'll be able to create the animation, and within 20-30 seconds you can get it. You can also download it as a GIF animation or download it as MP4. If you on the left side here, everything is downloaded somewhere here, so you can download this one to the computer, right? So I guess you must have seen some of this on the TV or on social media. So now you know how to create it, right? So next time if there any hurricane coming, you can go online and then just run the notebook, change the date, and change the bounding box to whatever the area you want to see. then you'll be able to create this easily. Besides using the data, so Google Search Engine also has the file products. So that means you can use the Ghost dataset to capture the wildfire, but you can also delineate the wildfire boundary. Basically, you can do an analytics on top of the images. And let's see. And this one, like I said, the data is very intense because it's high tempo frequency every couple of minutes. So it's a lot of data. If your area is too big or the time frame is too long, you might exceed the memory. But take a look at this one. This is the last animation I'm going to show you. This is the wildfire. And you will see the pink color here. This one actually delineates the wildfire boundary on top of the wildfire. So you can not only do visualization, you can also run analytics. And this is very powerful because you can see how the wildfire, the evolution of the wildfire. And you can also, integrate into some map. This is actually integrated in Google Map. So if wildfire is happening, when you search Google Map, it's going to ask you like showing this, and then to not take, to avoid getting stuck somewhere in the wildfire. So avoid some of those roads that's being closed or impacted by the wildfire. Okay, so that's all I want to show you is how you can run this kind of analysis, and then you can use this function to quickly create some animation. And the last section here is a little bit more advanced. I will keep it here. You can try it out. But essentially, after you use Google Assistant Cloud Computing, you develop some data products you want to share with other people. You can convert your algorithm into interactive web app, and then you can send the link to other people so that they don't have no coding. They don't need to have a Google Assistant account. They can access your data products. So here, if you want to try it out, you can take a look at the instruction here to build interactive web app. And also showing application here. If you click link, it will take you to this one. So this is called developed based on, it's called Solara. So you will see here right now, we're not running the code anymore. This is more like applications. So I turn the source code from the notebook into application. So anyone can try it out, right? So I can also full screen, I can zoom in, I can zoom out. So right now, this is an interactive web app that anyone can use. They don't need to have a Google Search Engine account. They don't need to know how to do coding. You do the coding, you develop the web app, and after that, and they can just try out your data set. And also, for example, I can also use the inspector, right? So the same thing is very much similar to what I showed you earlier in Jupyter, in Google Colab. But right now it's running on the web and it's developed using Python. So if you're interested in doing something like this, you're welcome to follow the instruction here and look at the application and to see if you want to develop something like that. So here, instruction, and if you click here, so here shows you the step-by-step instruction how to turn your source code into easy to use web app, so they can make your things more accessible, and people, as long as they have internet, they can try it out, and you can design what they want to run, the computation and also the interactive widget. Okay, so that's all I want to show you this afternoon. I hope you learned something new, and like I said, everything is reproducible, so you can go back to run the source code again. If you run into any errors, you can let me know, and other than that, try to adapt this to your area, your region of interest, and then see how it works, and try to compare, like if I don't use this, if I do it in a traditional way, how long it's going to take you. And I hope you see the power of cloud computing, and I hope you are convinced now to use this and also use Python and how to develop your own applications, how to access the data. So essentially now you can watch any movie for free by saying Geospatial. You can analyze any movie for free. You can run all the analytics by free in Geospatial data. Okay, thank you very much for your attention, and if you have any question, happy to answer your questions. Yeah.